Grounding and bonding. Grounding. Generally speaking, the difference between grounding and bonding is grounding is a direct connection to the earth to aid in removing damaging, transient overvoltages due to lightning. Bonding ensures the electrical continuity of the fault circuit path to provide the capacity and ability to conduct safely any fault current likely to be imposed, and to aid in the operation of the overcurrent protection device. Properly bonding all metal parts within an electrical system helps ensure a low-impedance fault current path. The issue of grounding and bonding confuses many inspectors. Due to its complexity, in this section, we will try to break it down to its fundamentals and look at the basic requirements and common failures that can lead to unsafe conditions around the home. Grounding. Let's start at the beginning of the electrical service. The last stop on the utilities distribution chain before the supply goes to the building is the transformer. This steps the high-voltage primary distribution down to the neighborhood to the 240-120-volt feeds to the homes. On a typical 240-120-volt service drop, we will have 2 ungrounded conductors and a single grounded conductor. This means that we have to establish our own grounding electrode system at the house. Refer to the illustration within the course and check the 3 grounding electrode conductors coming from the main panel. One connects to the metal water pipe, another connects to the driving ground rod, the third connects to a copper wire inside the concrete. This is critical for removing dangerous voltages imposed on the system via lightning strikes and overvoltage surges from higher voltages on power lines. If a grounding rod, pipe, or plate electrodes are used, they must have a rating of 25 ohms or less. Otherwise, an additional electrode must be added per section 250.56 of the NEC. Grounding electrodes. A grounding rod, footing reinforcing steel, and metal underground water pipes are examples of grounding electrodes, which are metal electrically conductive terminals through which current enters the earth. Refer to the illustration Grounding and Bonding within the course to identify the grounding electrode or rod and the grounding electrode conductor connected to the grounding or neutral bar at the main electric service panel board. At the main electric service panel board, with the integral main disconnect, you can see in the illustration the main bonding strap or main bonding jumper, also referred to as MBJ. There are several methods of connecting the grounding system to the ground, with a driven grounding rod being the most common in most areas. Most residential construction requires 2 separate grounding electrodes in any combination of the following, which need to be at least 6 feet apart: driven rods, rod-type grounding electrode rods, metal water pipes, well casings, Ufer grounds, ground plates, steel framing, and ground rings. Historically, the grounding system had just one connection to ground, and this was nearly always made on the water supply pipe. However, 2 connections are now required by most jurisdictions to ensure a low impedance ground, or one with little resistance. Because most utility companies now install plastic, potable water supply lines, a water pipe cannot be used as a grounding means, so one of the other electrodes listed must be used. It is also important to note that all electrodes that are present in the dwelling must be bonded together to form a single and complete grounding electrode system. Typically, the 2 required grounding electrodes need to be at least 6 feet apart. If one is the water pipe ground and the supplemental is a ground rod, another ground rod may need to be added in order to meet the requirements of Section 250.56 of the NEC. Gas piping should not be used as a grounding electrode for safety reasons, but in most areas, gas lines are required to be bonded to the grounding system if they are likely to become energized. Grounding electrode rods. 5/8-inch diameter. Rods made of stainless steel and copper or zinc-coated steel shall be at least 5/8 of an inch in diameter. Grounding electrodes of pipe and conduit must be at least 3/4 of an inch. Metric designator 21. There are special listed rods, and listed rods may not be less than 1/2 inch in diameter. If pipe or conduit is used as a grounding electrode, it must also be no less than 8 feet in length and no smaller than trade size or 3/4 of an inch. If a micrometer or similar device is not available, the home inspector shouldn't guess the rod's diameter. If visible, You may be able to confirm the diameter by looking at the listing marks, which may indicate that the rod complies with the diameter requirements of the National Electric Code, or NEC. The listing agencies CSA, ETL, MET, and UL will mark rods that are greater than 1/2 an inch in diameter and that have the correct minimum amount of coating. 8 feet in length and in the soil. Rod and pipe electrodes must be at least 8 feet in length to be considered a grounding electrode. All rods should be driven 8 feet into the earth. The rod and pipe electrodes must be installed at least 8 feet of length in direct contact with the soil in the ground. They must be driven into the ground at least 8 feet. They could be driven at an angle, but the angle should not be more than 45 degrees off the vertical. Or the rod could be buried in a trench that is at least 30 inches deep. Sometimes, in very rocky earth, the rods cannot be driven perpendicular to the ground, so they may be driven at an angle of less than 45 degrees. If they cannot be driven at all due to unfavorable soil conditions, they can be installed in a trench no less than 30 inches deep. But no part of any grounding electrode can be closer than 6 feet to any other. The upper end of the electrode should be flush with the ground or just below the ground surface so that the end and attachment are protected from damage. If you find a rock sticking up out of the ground, that's a defect. It should be at or just below the soil surface. Corrosion. Pipe or conduit made of steel shall have an outer surface that is galvanized or otherwise metal-coated to resist corrosion. If the material is iron or steel, the electrode must have its outer surface galvanized or metal-coated for corrosion protection. Attachment. The ground wire, the grounding electrode conductor, needs to be fastened, referred to as the attachment, with the correct approved clamp, and the attachment needs to be rated for direct burial if located below ground. It is common to see these acorn clamps installed improperly, with the conductor clamped under the screw rather than to the solid part of the clamp, which has the biggest contact area. Metal water pipes. Connecting to the main metal water pipe in a house was the most common type of connection at one time. Where the metal pipe is used as a grounding electrode, the conductor should be connected with clamps rated for water tubing and needs to be connected within the first 5 feet of piping as it enters the structure. Since the water meter is a removable part of this potential circuit, a jumper cable needs to connect the pipework on either side of the meter to ensure continuity at all times. Jumper at the water meter. A jumper or bonding conductor is a conductor used to ensure that there is electrical conductivity between metal parts that are required to be electronically connected. For example, a jumper may be installed over the water meter because the continuity of the grounding path or bonding connection of the interior pipes should not rely on the water meter. The jumper is a large gauge conductor that jumps over the water meter and is securely attached to the metal water pipe on each side. Well casings. As wells are bored to a great depth and lined with metal sleeves, they make good grounding electrodes, as long as they are far enough away from other grounds and are properly connected. Ufer Grounds. More properly referred to as a concrete-encased electrode, the Ufer Ground is named after Herbert George Ufer, a retired Underwriters Laboratory vice president who developed the system during World War II to help ground concrete armament bunkers. With so many homes and commercial buildings now built on concrete, steel-reinforced slabs, this grounding system has become very common. The requirements for Ufer Grounds are that they have either 20 feet of number 4 rebar or 4-gauge copper wire embedded in at least 2 inches of solid concrete within the footer that is in contact with the earth. This system must also have an external means of connecting other grounded systems to it, such as telephone wires. Ground plates. In some cases, ground plates are used as the grounding system, but this is uncommon in residential construction. Ground plates made of ferrous metal, such as iron or steel, shall have a thickness of no less than 1/4 inch. Plates made of non-ferrous metal should have a thickness of no less than 0.06 inches. They should be at least 2 square feet in overall size and be buried to a depth of 30 inches. Steel framing. Steel-framed buildings typically use the frame as one of the grounding electrodes as long as the structure is substantial enough and has at least 10 feet of connection to the earth. Most commonly, the framing is connected to an Ufer ground. Ground rings. Again, although it's very rare in residential construction, a ground ring may be installed where a minimum 2-gauge conductor is buried to a depth of at least 30 inches right around the structure. Grounding electrode conductors. The grounding electrode conductor, GEC, is a conductor that connects the system grounded conductor or the equipment to a grounding electrode or to a point on the grounding electrode system. The GEC is copper, aluminum, or copper-clad aluminum. It is not intended to carry current except in case of a ground fault. It can be bare and without color. Its size is related to the amperage of the service entrance SE conductors. Please refer to the table within the course that shows the sizes of the GEC. Remember, the GEC should be connected only to the neutral at the service panel, the panel containing the service disconnect, and nowhere else. The GEC is usually connected to the grounded service conductor or neutral service conductor in the service equipment where the main disconnect is located or in the meter enclosure. The grounding electrode conductor, or GEC, and the grounded service conductor are bonded together to the metal service enclosure by the main bonding jumper, screw or jumper connecting the neutral bus bar to the cabinet enclosure. The equipment grounding conductors, the grounding wires, are also brought to this point and tied to the grounded service conductor or neutral conductor and to the grounding electrode conductor, GEC. The other end of the grounding electrode conductor is connected to one or more grounding electrodes such as an underground water pipe and ground rod. Rod and pipe electrodes must be at least 8 feet in length to be considered a grounding electrode. The rod and pipe electrodes must be installed at least 8 feet of length in direct contact with the soil in the ground. No part of any grounding electrode can be closer than 6 feet to any other. The upper end of the electrode should be flush with the ground or just below the ground surface so that the end and attachment are protected from damage. If you find a rod sticking up out of the ground more than just a couple of inches, that's a defect. It should be at or just below the soil surface. Surge protector. Whole house surge protectors should be installed on new panel boards. A surge protector protects the home circuits in the event of a power surge through the service conductors, such as from a lightning strike. They are frequently seen added to existing panel boards. These devices are typically connected through a dedicated 240-volt breaker. They cannot be double-tapped into an existing 240-volt breaker. There is an inspection image posted by InterNACHI member Yasadel Martin on InterNACHI's public forum, forum.nachi.org, of a double tap at the main disconnect terminals or lugs. The terminals are not rated for 2 conductors, especially of different sizes. There is usually an indicator LED light that indicates the proper function of the surge protector. Most surge protectors are sacrificial or single-use devices. If there is a large power surge, the surge protector dies, protecting the system, and must be replaced. If the LED is not glowing, typically green, then the surge protector should be reported as needing replacement.